The real reason Saturn's rings are slowly dying right now across millions of years. Tonight, I want to tell you something about Saturn that almost nobody knows. The rings around Saturn are not a crown carved into the planet. They are a crown slowly falling back onto the world that wears it. Right now, every second. We have measured this. In this video, we will walk through how it is happening, how much time is left, and one strange fact at the end that surprised me the first time I read it. By the end of tonight, you will understand exactly why we are lucky to see Saturn's rings at all. So get yourself comfortable. Pull a blanket over you. Make whatever warm drink helps you settle. And let the lights go low. Let your shoulders drop. Let the room go quiet. We're going to take our time with this one. Before I begin, if you find these kinds of long, quiet science walks useful, take a second to subscribe, so these videos can reach more people who would love them. It is a small thing for you, but it makes a real difference for me. The algorithm pays attention when you do, and it helps this kind of slow, careful science find the people who would benefit from it. Now, let's begin. Take a moment and picture Saturn in your head. Just the basic image. The yellow planet. The pale rings going around it. The shape every child draws when you ask them to draw a planet. That picture is older than any of us. The first person to see Saturn through a telescope was Galileo Galilei in 1610. He pointed a small wooden tube with a lens at the night sky, and he saw something he could not understand. There were two strange lumps, one on each side of Saturn. He thought maybe Saturn had ears, or two small companions. He drew it as three connected dots in his notebook. It took another 45 years for someone to figure out what those lumps were. In 1655, a Dutch astronomer named Christian Huygens used a better telescope. He saw the truth. Saturn does not have ears. It has a flat ring, going all the way around the planet, like a thin disk. He wrote about it in code, in case he was wrong. Then, when he was sure, he announced it. That was 370 years ago. And in those 370 years, the rings have been the most famous feature in our solar system. Children draw them. Movies show them. Every picture of Saturn, from the first hand-drawn telescope sketches to the photographs taken by spacecraft last year, shows the same shape, a planet with rings. So when I tell you the rings are temporary, your brain pushes back. The rings have been there our whole lives. They were there when our parents were children. They were there when the first telescope was built. They were there when humans first walked out of Africa, hundreds of thousands of years ago. They feel as permanent as anything in the sky can feel. Think for a moment about how rare it is in nature for something to feel that permanent. Mountains erode. Coastlines change. Rivers move their courses across centuries. Even the stars in the sky shift their positions slowly over thousands of years. Almost nothing in the visible universe is genuinely fixed. Permanence, when we feel it, is almost always an illusion of short timescales. We feel Saturn's rings as permanent for the same reason we feel a tree as permanent. We do not live long enough to see them change. The tree was here when we were born. The tree will probably be here when we die. The fact that the tree is growing, slowly, every day, that the bark is shedding and new layers are forming underneath, does not feel like change because it is too slow. Saturn's rings work the same way, only on a much longer time scale. They feel permanent because we cannot see the change. But the change is happening. And yet, here is the truth I want you to hold tonight. The rings around Saturn are not a crown carved into the planet. They are a crown slowly falling back onto the world that wears it. Every second. Right now. As you sit there listening to me. And we know this not because of a guess. We know it because of a small piece of detective work that started in 1981, when a spacecraft called Voyager 2 flew past Saturn and saw something nobody could explain. That is where the story really begins. Before we get to Voyager, I want to make sure you understand what the rings actually are. Because most people, when they imagine Saturn's rings, picture something solid, like a flat plate, or a ribbon wrapped around the planet. They are neither. The rings of Saturn are made of pieces. Trillions of pieces, and every single piece is its own tiny moon, going around Saturn on its own little orbit. Let me give you a simple way to picture this. Imagine a swarm of bees flying in a circle. From far away, the swarm looks like one solid ring. You can see its shape. You can see its edges. But up close, It is not solid at all. It is millions of individual bees, each one flying its own path, all of them going the same direction. That is what Saturn's rings are. Except instead of bees, the pieces are made of ice. Mostly water ice. The same kind of ice you have in your freezer. About 70 to 90% of every ring particle is water ice. The rest is rocky material, mostly silicates, the same kind of stuff that makes up sand and dust on Earth. And the sizes of the pieces are wild. Some pieces are smaller than a grain of dust. Some are the size of marbles. Some are the size of cars. Some are as big as a mobile home, the kind of trailer you would see parked on the side of a highway. All of them, every size from dust to mobile home, are flying around Saturn at high speed, in the same direction, in the same flat plane. Now here is the part that is hard to imagine. The rings are huge. They reach out to about 282,000 kilometers from Saturn. That is more than 2/3 of the distance from Earth to our moon. If you put Saturn where the Sun is, the rings would stretch almost all the way to Mercury. And yet they are flat, almost impossibly flat. In most places, the rings are only about 10 meters thick. 10 meters. That is the height of a 3-story building. Imagine a sheet of paper the size of a city. That is the proportion. Something so wide it would dwarf entire planets, and so thin it could be flattened by a tall building. Why are they so flat? Because of the same reason the planets in our solar system all sit roughly in the same plane. Things that go around something tend to flatten out over time. Particles that are not in the flat plane get bumped, collided with, and slowly nudged into the flat plane. After enough time, everything ends up flat. The rings have been flattening for as long as they have existed. So that is the picture. A swarm of ice chunks, trillions of them, each going around Saturn at its own speed, all flattened into a thin disk wider than the gap between Earth and the Moon, wrapped around a planet you could see with your bare eyes from a backyard if you knew where to look. And every piece in that swarm is moving. Some of them are moving in ways that are very slowly, very patiently, taking them out of the rings forever. That is the part we have to understand next. In August of 1981, a small spacecraft called Voyager 2 flew past Saturn at high speed. It had been launched 4 years earlier from Cape Canaveral in Florida on a tour of the outer planets. It would eventually visit Jupiter, Saturn, Uranus, and Neptune. Today, it is the second human-made object that has ever left the solar system. The first was its sister spacecraft, Voyager 1. When Voyager 2 went by Saturn, it took thousands of photographs. Most of them showed exactly what scientists expected. The planet, the rings, the moons, the familiar shapes that humans had been drawing for centuries. But in some of the photographs, in the images of Saturn's atmosphere, there was something nobody could explain. 3 thin dark bands encircling the planet at northern mid-latitudes. 3 bands of darker color in the upper atmosphere, going all the way around Saturn, parallel to the equator, but offset to the north. They did not match anything else in the pictures. They were not weather patterns. They were not shadows from the rings. They were not the kind of thing you see on Jupiter or Earth or Mars. They were just there. 3 dark stripes running around the upper atmosphere of Saturn, and nobody knew why. For 5 years, those dark bands sat in the data. Scientists looked at them, argued about them, could not figure them out. Saturn was already a strange planet, with its own list of unsolved mysteries, and the dark bands joined the list. Maybe they were a chemistry thing. Maybe they were a season thing. Maybe they were something specific to Saturn that we just did not understand yet. And then, in 1986, an astronomer at NASA Goddard Space Flight Center named Jack Connerney published a paper. The paper was short, the argument was clean, and it answered the question of the dark bands in a way that, when you read it now, feels obvious. But at the time, it was a quiet revelation. Connerney said the dark bands were caused by Saturn's magnetic field. He said charged ice particles, electrically charged grains of water ice from the rings, were riding down invisible magnetic field lines and crashing into the upper atmosphere. The places where the field lines came down to the atmosphere were the places where the dark bands appeared. The ice was raining out of the rings into the planet, and we were seeing the splash marks. That paper, in 1986, was the first time anyone in modern science said the words ring rain. And to understand what ring rain is and why it matters, we have to take a small detour. We have to talk about magnetic fields, because without understanding the basic shape of a magnetic field, the rest of tonight does not make sense. So let me show you a magnetic field with a fridge magnet. Find a magnet, the kind you stick on a fridge. Now imagine sprinkling some iron filings, the small metal shavings, on a sheet of paper. Hold the magnet underneath the paper. The filings on top of the paper will not stay scattered. They will line up. They will form curved lines, going from one end of the magnet to the other, from the north end, around through the air, and back into the south end. Those curved lines are the magnetic field. The magnet has a force around it. The force is invisible, but the iron filings make the force visible by lining up along it. This is how every magnetic field works. The lines come out of one pole, called the North Pole, curve around through space, and go back into the other pole, called the South Pole. Anything in space that has a magnetic property, or that has an electric charge on it, will feel the force along those lines. Now scale that picture up to a planet. Saturn has the same kind of magnetic field as the fridge magnet, generated by movement of fluid metal deep in its interior. The lines come out of Saturn's North Pole, curve all the way around the planet through space, and dive back into Saturn's South Pole. The shape is the same, just enormous. Saturn's magnetic field reaches far out into space. It extends past the rings. It extends past some of Saturn's moons, the lines you cannot see with your eyes. The same kind of lines the iron filings showed us on the paper fill the space around the planet. And here is the rule that connects everything tonight. Anything with an electric charge, in the presence of a magnetic field, gets pulled along the field lines. The charged thing cannot just move freely through space. It has to slide along one of those invisible curved lines, like a bead on a wire. This rule has a name. It is called the Lorentz force, and it is one of the most basic ideas in physics. The picture from the fridge magnet, the iron filings showing the curved lines, is exactly what is happening at planetary scale. Anything charged in that space rides those lines. So now we know what a magnetic field is, and we know what it does to charged particles. We have one more piece to add. We have to figure out how the ice in Saturn's rings becomes charged in the first place. Because if the ice is not charged, the magnetic field does nothing to it. The ice just sits in orbit like a normal moon. It is the charging that turns the ice into a slide ride. Plain ice is not charged. If you take an ice cube out of your freezer and hold it near a magnet, nothing happens. The ice is electrically neutral. The atoms inside it have the same number of positive and negative charges, balanced out, and there is no extra charge for a magnet to grab. So how does the ice in Saturn's rings end up with an electric charge? The first way is sunlight. The sun is far away from Saturn, much fainter than it is from Earth, but it still hits the rings. And some of the sunlight that hits the rings is ultraviolet light, the kind of light that is more energetic than visible light. When ultraviolet light hits a piece of ice, it can knock electrons off the surface. An electron is the smallest negative charge in nature. When you knock one off, the ice particle is left with a tiny positive charge. This process is called the photoelectric effect, and it is the same process that makes solar panels work on Earth, just running in a different direction. The second way is the solar wind. The sun does not just give off light. It also gives off a constant stream of charged particles, mostly protons and electrons, blowing outward through the solar system at high speed. We call this stream the solar wind. When it hits Saturn's rings, some of those particles stick to the ice. Some knock more electrons off. Either way, the ice ends up with a net charge. The third process involves plasma. Plasma is a state of matter where atoms have been broken apart into freely moving charged particles, like a gas of bare electrons and ions. Saturn has a thick environment of plasma around it. Some of it comes from one of Saturn's moons, called Enceladus, which sprays water out of cracks in its surface. The water freezes, breaks apart, gets charged, and forms a cloud of plasma around Saturn. The ring particles, sitting inside that cloud, pick up charges from it. Now, none of these processes give the ice a big charge. Each ice particle ends up with only a tiny electric charge, far smaller than what is needed to give you a static shock when you touch a doorknob. But it does not need to be big. A tiny charge is enough to make the magnetic field grab the particle. And once the particle is grabbed, the rules change. A normal ice particle, with no charge, just orbits Saturn the way a small moon orbits a planet. It follows the law of gravity. It traces out a circle, or a small ellipse, around the planet. It stays in the rings forever, more or less. But a charged ice particle, in Saturn's magnetic field, does not follow gravity alone anymore. It follows two forces at once. Gravity is pulling it sideways, in its orbit around the planet. The magnetic field is pulling it along the field lines. And the magnetic field, near the rings, has lines that curve down toward the planet. So the charged particle starts to slide, out of its orbit, down along the line, toward Saturn's atmosphere. That is the moment the ice leaves the rings. Not because something violent happened, not because something hit it, because it picked up a tiny charge, and the invisible curved lines around Saturn became a one-way slide. And once the particle is on that slide, it does not stop until it hits the upper atmosphere of Saturn, thousands of kilometers below. That is ring rain. That is the mechanism the dark bands in 1981 were showing us. Now I want to give you the numbers, because the numbers are bigger than you would expect. In 2018, an astronomer at NASA Goddard named James O'Donoghue led a study that measured how much water was raining out of Saturn's rings every second. He used data from a giant ground telescope in Hawaii, called the Keck Observatory, to look at the upper atmosphere of Saturn and see how much water was crashing into it. The number that came back surprised him. The rings are losing about 10,000 kilograms of water every second. 10,000 kilograms. That is the weight of 3 or 4 cars, every single second, raining out of the rings into Saturn's upper atmosphere. Let me give you that number in a different way. O'Donoghue described it like this. Imagine an Olympic-sized swimming pool, the kind you see in the Olympics, full of water. The rings of Saturn lose enough water to fill that swimming pool every 30 minutes. Every 30 minutes. While we have been talking, since you started this video, an Olympic-sized swimming pool of water has fallen from Saturn's rings into the planet. By the time tonight's video is over, several more pools will have fallen. By tomorrow morning, dozens more. Let me give you the rate in another way. Picture a normal kitchen tap, the kind in your sink, turned on at full pressure. The water that comes out of that tap, in 1 hour, is something like 60 liters. Saturn's rings are losing about 10,000 kilograms of water every second. That is the equivalent of running 10,000 kitchen taps at full pressure, all the time, all going down into the planet, constantly, for hundreds of millions of years. Or think about it as weight. 10,000 kilograms is the weight of a small school bus. A small school bus, every second, made of water, falling out of the rings. 60 school buses every minute. 3,600 every hour. 86,000 every day. By the time you finish breakfast tomorrow, an amount of water roughly equal to a small lake will have fallen from the rings into Saturn. And this is just the steady classical ring rain. The number does not include the equatorial inflow that Cassini found in 2017, which we are about to talk about. The classical rain alone, before adding anything else, is enough to drain the rings within a few 100 million years. Now, this loss has been happening at this rate, more or less, for as long as the rings have existed, and it cannot keep happening forever, because the rings only have so much mass. Eventually, the rings will run out of ice to lose. How long do they have? O'Donoghue did the math. If you take the current loss rate, 10,000 kilograms of water per second, and you divide it into the total mass of the rings, you get a number. The rings will be gone in about 300 million years. 300 million years. That sounds like a long time, and on a human scale it is. It is longer than mammals have existed on Earth. It is longer than most of the species that have ever lived. But on a cosmic scale, it is short. Saturn itself is over 4 billion years old. The Sun is about the same age. The rings, at this rate of loss, will be gone in less than 1/10 of the time the planet has already existed. And that number, 300 million years, is the slow estimate, the optimistic estimate. There's a faster estimate too, and it comes from another piece of data, taken in 2017, in the final months of one of the most beautiful spacecraft missions in human history. We have to talk about Cassini. In 1997, a spacecraft called Cassini launched from Cape Canaveral, headed for Saturn. It took 7 years to get there. By the time it arrived in 2004, It was the largest, most expensive, most ambitious spacecraft humanity had ever sent to the outer solar system. It carried 12 scientific instruments. It carried a small landing probe, called Huygens, that would be released to land on Saturn's moon Titan. The mission was a partnership between 3 space agencies: NASA, the European Space Agency, and the Italian Space Agency. It was, in every way, a flagship. Cassini orbited Saturn for 13 years. It took hundreds of thousands of photographs. It flew through the plumes of Enceladus, the icy moon. It dropped Huygens onto Titan and got the first pictures from the surface of an alien moon. It watched Saturn's seasons change. It watched the rings, every day, for over a decade, in more detail than anyone had ever seen. And in 2017, Cassini was running out of fuel. The mission team had a choice. They could let Cassini drift, eventually crashing into one of Saturn's moons, possibly contaminating a place that might host life. Or they could end the mission deliberately, by sending Cassini into Saturn itself, so it would burn up in the planet's atmosphere and leave no trace. They chose the deliberate ending. They called it the Grand Finale. From April to September of 2017, Cassini did something it had never done before. It dove between the rings and the planet. 22 times, it threaded the narrow gap between Saturn's atmosphere and the inner edge of the rings. The gap was only about 2,000 kilometers wide. Cassini went through it at 26 kilometers per second. Each pass took only a few minutes. Each pass was risky. If Cassini hit even one small piece of ice from the rings at that speed, the mission was over. Cassini made all 22 dives. The instruments collected data on every pass. Some of the data was about the planet. Some was about the rings. Some was about the gap itself, which had never been measured before. And then, on September 15th, 2017, Cassini did its final dive. Not a pass. A plunge. The spacecraft went into Saturn's atmosphere on purpose, transmitting data the entire way down until the friction of the upper atmosphere broke it apart. The mission ended at 11:55 in the morning Pacific time. The last signal arrived at Earth 83 minutes later, after traveling at the speed of light across more than 1 billion kilometers. The spacecraft died inside the same planet it had spent 13 years studying, and in its final months, it measured the way Saturn was consuming its own rings. Cassini was gone, but the data from those final dives, including the data from the Grand Finale, took years to analyze. And what scientists found, when they looked carefully, was something nobody expected. Here is what the Cassini Grand Finale data showed. While the spacecraft was diving through the gap between the rings and the planet, the instruments measured something that was not classical ring rain. Classical ring rain, the kind we have been talking about, drops charged ice into Saturn at northern and southern mid-latitudes, where the magnetic field lines come down. That is the slow, steady rain that gives the rings about 300 million years of remaining life. But Cassini, on its dives through the gap, measured a separate stream of material falling straight down at the equator. Not charged ice riding magnetic field lines, just neutral material, ring particles and gas, plunging directly into Saturn's atmosphere from the inner edge of the rings. The amount was much larger than expected. The estimates from Cassini's measurements ranged from about 4,800 kilograms per second to as much as 44,000 kilograms per second. Compare that to the 10,000 kilograms per second from the classical ring rain. The equatorial flow could be many times bigger. And here is the part to be careful about. We do not yet know if the equatorial flow is steady, or if it was a temporary thing happening only when Cassini was watching. The Cassini Grand Finale only lasted a few months. We did not have time to measure the equatorial flow over a long period. It could be the normal state, in which case the rings have much less time left than we thought. Or it could be a temporary surge, in which case the older estimate of 300 million years is closer to right. If the equatorial flow turns out to be the normal state, the math changes dramatically. Instead of 300 million years, the rings might have less than 100 million years left. James O'Donoghue, the same researcher who measured the classical ring rain, looked at the Cassini equatorial data and said the combined loss rate could leave the rings with under 100 million years to live. So the honest range today is somewhere between 100 million and 300 million years. Maybe a little more, maybe a little less, depending on which measurements you trust and how the equatorial flow turns out to behave over longer time scales. Either way, the rings are temporary. Either way, on a cosmic time scale, they are vanishing fast. The most generous estimate gives them about 7% of Saturn's age. The most aggressive estimate gives them about 2%. In either case, the rings are not a permanent feature of the solar system. They are a phase the planet is currently going through. And we have only been able to measure this because of one spacecraft, threading a narrow gap 22 times before flying into the planet to die. There's something quietly beautiful about that. The grand finale told us how the ending begins. There's something quietly important about how this measurement was made. We did not see the equatorial flow from Earth. We did not see it from any orbit Cassini had used in the previous 13 years. We only saw it because the spacecraft was flying through the gap between the rings and the planet, where no spacecraft had ever flown before. The data was unique to those final months. That means we have very few measurements of the equatorial flow. The full picture comes from a few months of dives, in 2017, just before Cassini was destroyed. To know whether the flow is steady, or whether it varies over years and decades, we would need another spacecraft to go back and measure again. We do not have one yet. When ice rains out of Saturn's rings, it does not just float gently into the planet. It hits the upper atmosphere at high speed, hundreds of kilometers per second, and the upper atmosphere of Saturn is hot, much hotter than the cloud tops most people picture when they think of Saturn. Let me give you the picture. Saturn has a thick atmosphere, mostly hydrogen and helium, like a small, cold version of the Sun. The visible cloud tops, the ones you see in pictures, are at the bottom of the atmosphere. They are cold and pale. But above the cloud tops, there is a layer called the stratosphere. And above the stratosphere, there is a layer called the ionosphere. The ionosphere is where the ice from the rings ends up. The ionosphere is not really a place. It is more like a state. It is a layer of atmosphere where the air is so thin and the radiation from the sun is so direct that the gas atoms have lost some of their electrons. They have become charged. They are no longer neutral atoms. They are ions. That is where the name comes from. Ionosphere, the layer of charged atoms. On Earth, we have an ionosphere too. It is the layer that bounces radio waves around the planet. It is where the auroras happen. It is the same kind of layer Saturn has, just much smaller and lower density. The ionosphere of Saturn is about 2,000 kilometers above the cloud tops, and it is hot, around 1,000 Kelvin, which is about 730 degrees Celsius, hot enough to melt aluminum. So when an icy particle from the rings, riding down a magnetic field line, finally enters the ionosphere, it does not survive. It vaporizes. Almost instantly, the water ice turns into water vapor. The vapor breaks apart into hydrogen and oxygen. The oxygen reacts with the gases already in the atmosphere. Within seconds, the ice particle is gone. It has become part of Saturn. Imagine an ice cube on a hot stove. That is what happens in fast motion, 2,000 kilometers above Saturn's clouds, as the ring rain hits the heat. This vaporization is what made the dark bands in the Voyager 2 images. The water vapor, breaking apart in the upper atmosphere, changes the local chemistry. It changes how light from below shines through. It changes the brightness, just slightly, of the air at those latitudes. From far away, the change looks like dark bands. The bands are not shadow. They are not weather. They are the chemical signature of a rain made of ice from rings, falling out of the sky and burning up in the air above the cloud tops. And once the ice is gone, it is gone. The water vapor mixes into Saturn's atmosphere. It will stay there, more or less, forever. The ring is shorter by exactly the amount of ice that fell. The next ring rain, the next dive of the next charged particle, makes the ring shorter again, and again, and again. We said earlier that the rings are a crown slowly falling back onto the world that wears it. Now you can finally see the actual mechanism that makes the line literal. Charged ice, invisible magnetic lines, a 2,000-kilometer slide, a vaporization in a hot ionosphere, the rings becoming planet. That is ring rain. That is what is happening every second while we sit here. I want to step back for a moment and zoom in on the rings themselves. Because when astronomers talk about Saturn's rings, they do not just mean one ring. They mean a system of rings, with named parts, with gaps between them, with structure that took centuries to figure out. Galileo, in 1610, saw the rings as two lumps. He could not even tell they were rings. The technology was too crude. Christian Huygens, in 1655, figured out it was a single flat ring. That was a huge step forward, but he still thought of it as one thing, one solid disk going around Saturn. Then in 1675, an Italian-French astronomer named Giovanni Domenico Cassini, the same Cassini that the spacecraft was named after, looked through a better telescope and saw something new. There was a dark gap inside the ring, a thin black line going all the way around, dividing the ring into an inner part and an outer part. The gap is now called the Cassini division. It is about 4,700 kilometers wide. You can see it through a backyard telescope on a clear night, if your eyes are good and the conditions are right. Cassini's discovery told everyone that the ring was not one thing. It was at least two. There was an inner region and an outer region, separated by a clear gap. Over the next 200 years, as telescopes got better, astronomers found more structure, more gaps, more divisions, more named regions. Today, the main rings of Saturn are divided into three letter-named parts: the A ring, the B ring, and the C ring. The B ring is the brightest and densest, the one most people think of when they imagine Saturn's rings. The A ring is outside the B ring, brighter at its edges, separated from the B ring by the Cassini division. The C ring is the innermost main ring, faint and dusty, sitting just outside Saturn's atmosphere. There are also fainter rings, called the D ring, the E ring, the F ring, and the G ring, but the three main rings are the heart of the system. Now here is the part that connects this back to ring rain. The C ring, the innermost main ring, the closest one to the planet, is being lost first, because it is closest to Saturn. The magnetic field is strongest there, and the gravity is strongest there. The charged ice particles in the C ring are the easiest to pull down into the planet. The C ring is fading, particle by particle, faster than the other rings. In about 100 million years, if the current rate holds, the C ring may be gone entirely. Saturn would still have rings, but the inner edge would have receded outward. The familiar shape would change. A few 100 million years after that, the B ring would start to fade. Eventually, only a thin remnant of the outer A ring would be left. Eventually, even that would go. This sequence, inner rings disappearing first, then outer rings following, is what the NASA visualizations of future Saturn show. If you watch the artist illustrations of how Saturn might look in 50 million years, then 100 million years, then 200 million years, you see the rings shrinking from the inside out. The crown does not get smaller all at once. It loses its inner pieces first, then slowly the rest. And that order, inner to outer, is one more piece of evidence that ring rain is doing what we think it is doing. The pattern of loss matches the strength of the magnetic field. The pattern of magnetic field strength matches the geometry of Saturn. Every piece fits. Before scientists even understood what the rings were made of, they had figured out, with math alone, that the rings could not be solid. The work was done in 1857 by a Scottish physicist named James Clerk Maxwell. Maxwell is one of the giants of physics, the same person who later figured out the equations for electricity and magnetism. But before all of that, when he was a young man, he won a prize for proving something simple about Saturn's rings. The prize was called the Adams Prize, and the question was this: what are Saturn's rings made of, and how do they hold together? At the time, there were three possibilities people had argued about. Maybe the rings were one solid disk, like a flat metal plate going around Saturn. Maybe the rings were a fluid, like a thin sheet of liquid going around the planet. Or maybe the rings were a swarm of tiny pieces, each one orbiting Saturn separately. Maxwell looked at all three options, and with math alone, no telescopes, no spacecraft, just equations on paper, he showed that the first two were impossible. The solid disk, he showed, would not hold together. Saturn's gravity pulls harder on the part of the ring closest to the planet than on the part farthest from it. That difference in pull, that uneven force, would tear a solid disk apart. Within a short time, the disk would shatter. The fluid sheet, he showed, was almost as bad. The same uneven gravity, plus the way fluids flow, would break the sheet into waves and ripples that would tear it apart even faster. That left only one option. The rings had to be made of separate pieces. Each piece was its own little orbit. The pieces could ride alongside each other, all going the same direction, but they had to be individual things, not a connected whole. Otherwise, the math did not work. Maxwell published this argument in 1859. For over 100 years, it was considered a beautiful piece of theoretical work, but nobody had directly seen the individual pieces. The rings still looked like a smooth disk in every telescope. Then, starting in the 1970s and continuing into the 1980s, the Voyager spacecraft and later the Cassini spacecraft took close-up pictures of the rings. And what they showed was exactly what Maxwell had predicted more than a century earlier. The rings, up close, were trillions of separate pieces. The smoothness was an illusion of distance. The pieces were the truth. So when ring rain pulls one piece of ice out of orbit, it does not break a connected structure. It just removes one of trillions of independent particles. The rest of the ring keeps going, undisturbed by the loss. The ring just gets very slightly less dense in that one spot. Then more particles fill in. Then more leave. The math Maxwell did in 1857 set up the physics that lets ring rain happen at all. This is the kind of beautiful thing that happens in science. A piece of work done before electricity was understood, before atoms were proven to exist, before anyone had photographed Saturn at all, turns out to be the foundation for what we now understand about how the rings die. If you look at Saturn's rings up close, you see something strange. The rings have very sharp edges. The outer edge of the A ring is a clean line, not a fuzzy gradient. The Cassini division, the gap that Giovanni Cassini found in 1675, has clean edges too. The C ring has clean edges. The faint outer rings, the F ring and the G ring, have unbelievably sharp edges, considering they are made of trillions of independent pieces. Why are the edges so sharp? Why do the rings not just smear out into a single broad fuzzy disk? The answer is moons. Tiny moons. Saturn has small moons embedded in its rings, or just outside them, that act like sheepdogs herding a flock of sheep. They are called shepherd moons. There are several of them. Pan and Daphnis sit inside ring gaps, keeping the gaps clean. Atlas sits at the outer edge of the A ring, keeping the edge sharp. Prometheus and Pandora sit on either side of the F ring, squeezing it into a narrow strip. Here is how it works. A shepherd moon is just a small lump of rock and ice, a few kilometers to a few tens of kilometers across. It orbits Saturn like any other moon, but because it is sitting near a ring, its gravity reaches into the ring and pulls on the ice particles there. Particles that drift too close to the moon get pulled in or kicked away. Over time, the moon clears a path around itself, like a snowplow on a road. The moon is the plow. The ring is the snow. Where the moon goes, the ring is pushed back. Pan, for example, sits inside a gap called the Encke Gap. The Encke Gap is about 325 kilometers wide. Pan keeps it clean. Without Pan, the gap would fill in with ring particles within a short time, and the smooth shape we see today would be lost. So the rings are not just falling apart through ring rain. They are also held together, in their familiar shape, by tiny moons doing patient gravitational work every single orbit. The shepherds keep the sheep in line. Without them, the rings would be a uniform fuzzy disk, not the sharp-edged structure we know. And here is the next thing to understand. There is a limit, a specific distance from Saturn, where moons cannot exist. Inside that distance, any large moon would get torn apart by Saturn's gravity. The limit is called the Roche limit, named after a French astronomer, Edouard Roche, who figured out the math in 1848. Let me show you the Roche limit with a piece of dough. Take a ball of dough. Hold it in front of you. Now grab one side of the dough with one hand and pull. The dough stretches. If you pull hard enough, it tears in half. Saturn's gravity does this to anything it can reach. The side of an object closest to Saturn is pulled harder than the side farthest away. This uneven pull is called a tidal force. We talked about tidal forces in the Proxima b context, the same physics that locks planets to their stars. Here, the tidal force is what tears moons apart. Inside the Roche limit, the tidal force on a moon is bigger than the moon's own gravity holding itself together. So the moon stretches, and then it breaks, and then the broken pieces stretch and break again, until the moon is reduced to a swarm of small pieces, all in orbit, all flat. That is what the rings of Saturn are. They sit inside the Roche limit. They are made of pieces too small for tidal forces to break further. Each piece holds together because it is small enough that its own gravity does not matter. But anything moon-sized, anything big enough for its gravity to count, would be torn apart at this distance. So the rings are, in one way, the corpse of something. Maybe the corpse of a moon that came too close to Saturn and got destroyed. Maybe the corpse of a captured comet that wandered into Saturn's gravity well and could not escape. Maybe the leftover dust from when Saturn formed, never able to gather into a moon because it was inside the Roche limit from the start. Whatever they came from, the rings exist in the zone where moons cannot. They are the only kind of structure that can survive there. Pieces, not bodies. A swarm, not a body. Now we come to one of the biggest unanswered questions in modern planetary science. How old are the rings? When did they form? Are they as old as Saturn, billions of years old? Or are they young, maybe only a few 100 million years old, formed long after the planet itself? This question is genuinely unsettled. Different scientists, looking at the same data, come to different answers. I want to walk you through both sides, because the truth is, we do not yet know which side is right. Here is the case for young rings. The argument is called the pollution argument, and it goes like this. The rings are made of ice. Ice is naturally bright white, but space is not clean. There is dust everywhere in the solar system, fine dark dust from comets and ancient debris, drifting between the planets. Over time, that dust falls onto the rings and slowly darkens them, like fresh snow getting dirty over weeks of being outside in a city. If the rings were 4 billion years old, the same age as Saturn, they would have been collecting dust for 4 billion years. They would be very, very dark by now, almost gray, maybe even black in places. But they are not. Saturn's rings are still bright. They are mostly white, with subtle color variations, but nowhere near as dark as 4 billion years of dust accumulation should make them. So, the pollution argument says, the rings must be younger, maybe a few 100 million years old, maybe even younger than the dinosaurs. In 2023, a study led by Sasha Kempf at the University of Colorado Boulder pinned the age of the rings at no more than 400 million years old. They measured the actual rate at which dust was falling onto the rings, using an instrument that had been on the Cassini spacecraft. They calculated how much dust would have accumulated over different time spans. They concluded the rings could not be older than 400 million years, because if they were, they would be much darker than they are. That study, published in Science Advances, was the strongest case yet for young rings. It seemed to settle the question. The rings formed recently, in cosmic terms, possibly when dinosaurs were still walking the Earth. But then, in late 2024, a different study led by Ryoki Hayato, published in Nature Geoscience, challenged this conclusion. Hayato and his team argued that the dust falling onto the rings does not actually darken them as much as people had assumed. The micrometeoroids, the tiny dust grains that hit the rings at high speed, do not just stick. Most of them vaporize on impact. The dark material gets blown apart, scattered, dispersed. Very little of it actually contaminates the ice. If Hayato is right, then the pollution argument is weaker than it seemed. The rings could be old after all. They could have been around for billions of years. They could be the same age as Saturn itself. So now we have two recent, careful, peer-reviewed studies. One says the rings are no older than around 400 million years in age. The other says they could be 4 billion years old. Both teams are looking at the same general system. They are reaching opposite conclusions. This is what an honest scientific debate looks like. There is no winner yet. The data we have today supports both possibilities. We will need more data, more measurements, possibly another spacecraft, before we can settle it. What makes this debate so hard to resolve is that we cannot easily go look. We cannot send a sample of the rings to a lab and date it. The rings are made of small ice particles in a hostile environment that no current spacecraft is designed to land on or sample directly. Cassini got close. It flew through the gap. It sampled some of the dust raining out of the rings, but it did not land on the rings themselves. To definitively settle the age question, we would need a future mission, probably a small probe that could fly through the rings and bring back ice for direct laboratory analysis. No such mission is currently funded, but here is what I want you to take away. The age of Saturn's rings is still debated, but their loss is not. Whether the rings are in the 400 million year range or 4 billion years old, they are leaving. Ring rain has been pulling ice out of them at a measurable rate, every second, for as long as we have been able to measure. That part is not in dispute. Only the question of how long they have been here is unresolved. And in some ways, the age question, when it eventually gets answered, will not change tonight's story. The rings are temporary. They are slowly falling. We are alive in a window when they exist. That part is settled, regardless of how that window started. Now I want to bring everything together, because the title of this video promised the real reason, and I want to give it to you cleanly, in one sentence, before we widen out again. The real reason Saturn's rings are slowly falling into the planet is this. Saturn's gravity and Saturn's magnetic field, working together, are eating the rings. That is the whole answer. Two forces, one planet, a patient, billion-year process of consumption. Let me explain what I mean by that, because it holds the whole case together. The gravity, by itself, would just keep the rings in orbit, nothing more. Gravity is what holds the rings around Saturn in the first place. Without gravity, the rings would drift away into space. So gravity, on its own, is not the killer. It is the keeper. The magnetic field, by itself, would just be an invisible structure around Saturn. Field lines coming out of the North Pole, curving around through space, going back into the South Pole. Beautiful, powerful. But by itself, it does not pull anything in. It is when the two work together, gravity and magnetism, on charged ice, that the rings start to die. Here is the chain. Sunlight and plasma give an ice particle a tiny electric charge. The magnetic field grabs the charged particle and forces it onto an invisible curved line. Gravity, working at the same time, pulls the particle along the line, downward, towards Saturn. The particle slides down the line, faster and faster. It enters the upper atmosphere. It vaporizes. It is gone. Multiply that chain by trillions of particles, by every second of every day, for hundreds of millions of years, by every place around the planet where the field lines come down to the atmosphere. That is what is happening. The rings are not standing still. They are being slowly, patiently, mechanically eaten by the planet they decorate. Every second, 10,000 kilograms of ice. Every half hour, an Olympic-sized swimming pool of water. Every century, an amount of material that would dwarf the largest building humans have ever made. This is why the title says the real reason. Not because there's one single mechanism, like a flare or an impact. The real reason is bigger than that. The real reason is structural. Saturn was always going to do this to its rings. Anytime a planet has a strong magnetic field, and anytime it has a ring made of ice, the same thing will happen. Charged ice, field lines, gravity, slide, vaporize, repeat. Saturn is not a unique case. It is just the closest example of a universal process, and the rings are not a permanent feature of Saturn. They are a phase, a long, beautiful, temporary phase, in which a planet has a crown made of ice, and the planet is slowly, second by second, taking the crown back. The rings are not a crown carved into the planet. They are a crown slowly falling back onto the world that wears it. That sentence has been the spine of tonight, and now you know why. The crown is not stable. It was never stable. It was always going to fall. We are watching the fall happen, in slow motion, across geological time. That is the real reason. Gravity plus magnetism, working together, on charged ice, for as long as the rings exist. And the rings will not exist forever. Saturn is the famous one. But Saturn is not the only ring planet in our solar system. The other three giant planets, Jupiter, Uranus, and Neptune, all have rings too. Most people do not know this, because the rings on those planets are faint. So faint that they were not even discovered until spacecraft visited each planet up close, in the 1970s and 1980s. Jupiter has rings. They were discovered by Voyager 1 in 1979. Jupiter's rings are extremely thin and dusty, made mostly of small dust particles, not ice. They are so faint that you cannot see them through any backyard telescope. Even through a major observatory telescope on Earth, they are nearly invisible. We had to send a spacecraft to find them. Uranus also has rings. They were found in 1977 by accident, when astronomers were watching Uranus pass in front of a distant star. The star's light dimmed several times, in a regular pattern, before and after Uranus itself blocked it. The dimming was caused by 13 narrow rings, made of dark rocky material, going around the planet. They are dark, dim, and almost invisible from Earth. Neptune has them too. They were spotted in 1984, again by watching the planet pass in front of a distant star. They are even fainter than Uranus's rings. Some of them are not complete circles. They are arcs, partial rings that go only partway around the planet. We are still not entirely sure what holds them in place. So all 4 giant planets have rings, but 3 of them have faint, dim, mostly invisible rings. Only Saturn has the bright, dramatic, naked-eye visible spectacle. Why? Saturn's rings are different in 2 ways. First, they are made mostly of water ice, which reflects light brilliantly. The other planet's rings are made mostly of dark rocky material, which absorbs light. Second, Saturn's rings are massive, far more massive than the rings of any other planet. Some estimates put the total mass of Saturn's main rings at around 15 quintillion kilograms. That is a 15 with 18 zeros after it. The rings of Uranus and Neptune, combined, are probably less than 1% of that. So Saturn won the lottery. Among the 4 ring planets in our solar system, only Saturn has a ring system this bright, this massive, this visible. The other 3 have rings, but they are quiet, modest things. Saturn's are the spectacle. And here's the part that connects this back to tonight. The other planets' rings are also losing material, slowly, through similar processes. Jupiter's faint rings are constantly being replenished by dust kicked off small inner moons, by tiny meteorite impacts. If those moons stop supplying dust, Jupiter's rings would fade. The rings of Uranus and Neptune may be in similar states, fragile and fed by small moons that may not last forever. So the loss of rings is not unique to Saturn. It is a universal process. Every ring system in our solar system is in some kind of dynamic balance, with material being added and material being lost, and most of them are losing more than they are gaining. Most of them, eventually, will be gone. Saturn is just the most spectacular case, the most visible, the clearest example, and so the case we are walking through tonight, the slow erasure of a crown by gravity and magnetism, is not just about Saturn. It is about every ring in the solar system. It is about ring systems in general, probably about ring systems everywhere in the universe. Now I want you to imagine Saturn in 50 million years, not the Saturn of today, with its brilliant white rings reaching out 2/3 of the way to the moon. The Saturn of 50 million years from now. The C ring, the innermost main ring, is mostly gone by then. It has been raining into the planet faster than the other rings, because the magnetic field is strongest closest to the planet. What is left of the C ring is a thin, dim, almost invisible inner haze. The B ring, the brightest of the current rings, has shrunk inward at its inner edge. It is still bright, still the spectacle, but smaller than today. Maybe 2/3 the width it has now. The A ring is still there. The shepherd moons, Pan and Daphnis and Atlas, are still doing their work. The Cassini division is still visible. That is 50 million years. Now imagine 100 million years. The C ring is gone. Completely. Not even a haze. The B ring has receded much further. The Cassini division has widened, because the inner edge of the A ring has not moved much, but the outer edge of the B ring has fallen back. The whole system has thinned. Saturn still has rings, but they look different. Less imposing, less dramatic, a modest band rather than the wide, brilliant disk we know. Now imagine standing on Saturn's largest moon, Titan, 50 million years from now. Titan has methane lakes and a thick orange atmosphere. From its surface, Saturn fills a huge portion of the sky, much bigger than the moon looks from Earth. A creature standing on Titan and looking up at Saturn 50 million years from now would see a planet that, to it, has always had rings, but the rings would be visibly thinner than what we see today. the C ring would already be gone or fading. The picture in the sky would be different. Not less beautiful, just different. Now imagine that creature trying to imagine our era. The era when the rings were at their full bright extent. All three main rings clearly visible, brilliant against the dark of space. To that creature, our era would feel like a golden age. A time when the crown was at its widest, before any of the inner rings had vanished. A time the future moon dweller could only see in old data and pictures. The way we now look at pictures of vanished places. Now imagine 200 million years. Even the B ring is fading. The brilliant white density that defined Saturn for our entire telescope history is becoming patchy. Some sections of the B ring still hold their density. Others have thinned to gauze. The whole structure is starting to look more like the rings of Uranus or Neptune than like the rings we are watching tonight. Now imagine 300 million years. The rings are mostly gone. There are still small, thin, faint inner rings, sustained by occasional impacts on Saturn's inner moons. But the bright spectacle, the crown, is gone. Saturn looks like a yellow gas giant with a very faint inner haze. From Earth, with a telescope, you would see a planet without rings. The rings would not even be visible. This is what Saturn will look like in 300 million years, if the optimistic estimate is right. If the equatorial inflow is the normal state, this could happen even faster, maybe in 100 million years. And remember, 300 million years is short. It is a fraction of how long Earth has had life. It is far shorter than the time between the dinosaurs going extinct and now. A creature that lives on Saturn's largest moon, Titan, 300 million years from now, looking up at Saturn from the methane lakes, would see a planet without a crown. That is the future the data points to. Not as a guess, as a calculation, based on measurements we have already made. And this is what makes the moment we are in, right now, strange and rare. Saturn is over 4 billion years old. The Sun is about the same age. Earth is about 4.5 billion years old. The solar system itself, with all its planets, has been around for that whole time. And here is the question. How long, out of those 4 billion years, has Saturn had its bright visible rings? If Kemp's young rings argument is correct, the rings are no older than roughly 400 million years old. That is 1/10 of Saturn's life. Saturn has had rings for 10% of the time it has existed. The other 90% of Saturn's life, the planet had no rings, or only faint dim rings like Jupiter and Uranus and Neptune. And the rings will be gone in another 100 to 300 million years. So the total visible window, the era when Saturn has its bright crown, is somewhere between 500 million and 700 million years long. Out of 4 billion, about 1/8 of the planet's life, at most. If Hyoto's old rings argument turns out to be right, the window is longer. The rings could have existed for billions of years. But even then, the rings will not last forever. The end is coming. The end has been coming slowly, since the rings began. Now think about humans. Our species, Homo sapiens, has existed for about 300,000 years. Our civilization, with cities and writing and telescopes, has existed for about 10,000 years. Galileo first looked at Saturn through a telescope in 1610. Christian Huygens figured out the rings in 1655. We have been carefully studying Saturn's rings for less than 400 years. Out of the 800 million year window, give or take, when the rings have been visible, we have been here for the last 400 years. We arrived in the last fraction of that window. We arrived in time. Imagine the bad luck of arriving on the planet a billion years from now. Saturn would be a ringless gas giant. We would not even know it had ever had rings. We would be reading about them in old science papers, the way we read about extinct animals or vanished oceans, as part of a deep history we never witnessed. Or imagine the bad luck of arriving on the planet a billion years before the rings formed. In the case where the rings are young, Galileo's telescope would have shown a plain yellow gas giant. The whole imagination of children drawing planets with rings would never have existed. Saturn would just be a smaller, paler Jupiter. But we did not arrive then. We arrived now. We arrived in the precise window where the rings are still bright, still spectacular, still the most famous feature in the solar system. We arrived in time to see them. Think about that math for a second. The total visible window for Saturn's rings might be 800 million years. Out of those 800 million years, humans have existed for 1/25,000th of the window. We have had telescopes for 1/2 millionth of the window. The probability of a human, picked at random from across all of Saturn's ringed era, being alive at any given moment when humans exist, is vanishingly small. And yet here you are, listening to me describe this, looking up at the planet that did all of this. The fact that you are alive in the right window is not a deep cosmic plan. It is just a fact, but it is a fact that is rarer than you might think. And we will not see the end. The end is hundreds of millions of years away. No human alive today, no human born tomorrow, no human born in the next 1,000 generations will see the rings disappear. The fading will be too slow to notice on any human time scale. To us, the rings will look exactly the same as they have looked since 1610. Permanent, eternal, unchanged. That is the strangest fact of tonight. We exist in a window when we can see Saturn's crown, and the rate of disappearance is too slow for any of us to ever notice. From our perspective, the rings are forever. From a galactic perspective, they are a moment. This is what the astronomer James O'Donoghue meant when he said, after publishing his ring rain paper, that we are lucky to be alive at a time when we can see Saturn's ring system. Not lucky in some grand cosmic sense. Lucky in the simple sense that we showed up while the show was still on. And that is why I wanted you to hear this story tonight. Not because the rings will fall during your lifetime. They will not. But because once you know they are temporary, every photograph of Saturn becomes something different. It becomes a portrait of a planet during the rare, brief, beautiful era when it had a crown. An era that started before us and will end long after us. An era we are living through, even if we cannot feel it. There is one more thing I want to leave you with before we close. Something that is not exactly science, but that the science makes possible. We tend to think of beauty as a thing that exists. The Mona Lisa is beautiful. The Grand Canyon is beautiful. Saturn's rings are beautiful. We say it like the beauty is a property of the object, like its color or its weight. The thing simply is beautiful, and we look at it, and the looking is enough. But Saturn's rings teach us something different. They teach us that beauty can also be a verb, a doing, a happening. The rings of Saturn are not beautiful in some permanent, unchanging way. They are beautiful while they are still here. They are beautiful in the act of falling. They are beautiful in the same way a sunset is beautiful, or a song is beautiful, or a snowfall is beautiful. Because they are temporary, because they are passing, because the moment of seeing them is not the same as the moment after. The Saturn we look at tonight is not the Saturn that existed 500 million years ago. It is not the Saturn that will exist 500 million years from now. It is a snapshot, a frame, one particular configuration in a long, slow movie that has been playing for billions of years, and we get to see this frame right now with our backyard telescopes and our spacecraft in our eyes. We are part of the audience for the most beautiful temporary structure in the solar system, and the audience will only get to watch for so long before the show ends. This is what astronomers mean when they talk about cosmic luck. Not that anything was arranged for us. The universe is not arranged for us, but that we showed up by chance during a window when the universe is unusually beautiful in our particular corner of it. The window will close. The rings will fall. Saturn will become a ringless gas giant eventually, and any future intelligence in this solar system will look at our pictures of Saturn with rings the way we look at pictures of mammoths or of the Library of Alexandria, as something that used to be and is no longer. Closing. The crown and the world that wears it there is a planet in the southern sky. You have seen it your whole life. Yellow, calm, with rings reaching out across 2/3 of the distance to its largest moon. The most famous feature of the most familiar gas giant, the kind of planet that turns up on every list of cosmic wonders. Tonight we walk together through what is happening to those rings. The dark band's Voyager 2 photographed in 1981. Jack Connerney figuring out what they meant. Charged ice, magnetic field lines, the vaporization in the ionosphere. Cassini's Grand Finale, threading the gap before flying into the planet to die. The numbers, the age debate, the shepherd moons, the Roche limit, the structure falling inward from the inside out. And the real reason? Gravity and magnetism working together on charged ice for as long as the rings exist. Here's what I want you to take with you when you turn this off, or when you wake up halfway through and start the next part. The rings of Saturn are not a crown carved into the planet. They are a crown slowly falling back onto the world that wears it. Every second, for as long as we have been measuring, for longer than we have known, for longer than we will know. The next time you see a picture of Saturn, I want you to feel something quiet. The rings are there, but the rings are also leaving. The picture is a portrait of an era, not a forever. And we are alive in the time when the portrait still works. Beauty is a verb. The crown is real, and the crown is falling, and the world is slowly receiving its own crown back. There's no villain in this story. There's no catastrophe. There's just gravity and magnetism, doing what they always do, patient and unrelenting. And there is us, sitting here, watching the part of the show we get to watch. Lucky to be in the audience. Lucky to know what we are looking at. Good night from a small planet around a calm yellow star. 3 orbits in from the sun. Good night from a place where we still have the kind of luck that lets us look up and see Saturn with its crown still bright. If you enjoyed tonight, a small subscribe before you go means the next video finds you, and finds others like you who would love it. It is a small thing for you, and a real one for me, and it helps this kind of slow, careful science reach more of the people who would benefit from it. Good night from here, where the sky is kinder.